Can you hear me now? Sorry.
Yep.
Perfect.
And now it's full screen.
Wonderful. Yeah, I was having some technical issues. Thank you so much for inviting me to participate in this amazing conference. So I was asked to talk about Kilonova. So I thought I talked a little bit about the connections between cosmic alchemy and what we can learn from the light curve and the nucleosynthesis. And of course, this is work that I have done in collaboration with a lot of people here, which I'm incredibly grateful to have collaborate with. So let me give you just the outline of my talk. So I very briefly wanted to get us all on the same page about the R process, and there's been a lot of really beautiful discussion about this. So I just highlight a few aspects which I think are important to guide us to this discussion. I really want to emphasize the clues that we have derived from the abundance observations in stars and sort of the constraints that I actually put on the nucleosynthetic outputs that we're basically all trying to produce, and what are the constraints that can be derived from observations of stars in the Milky Way. I'll talk a little bit about the lessons from this beautiful event and what we have learned from short gamma ray burst. And I'll finalize giving you some thoughts about future prospects and where the field is moving. Okay, so neutron capture, as you see, what we see here is the S process and R process abundance in the sun. As you know, about half of the elements are made by one process, half of the elements are made by the other process, but both processes contribute with different amounts for a particular element. I really want to emphasize these three peaks that you see here, which of course are directly related to nuclear structure with the neutron closed shells. They basically don't match in mass number. But we'll talk briefly about why that's the case. And that's, of course, because the R process is made far away from equilibrium, and then it further decays back to stability. So the position of those closed neutron shells get erased as a function of time. But in general, this is basically what we derive from the sun. And I'll talk a little bit about what we have learned from these abundance distributions in stars, which is going to tell us something actually quite deep about how the nucleosynthetic process operates over the history of the universe. So just briefly, I think Jonas really gave an incredible talk about this. What I'm showing here is the stable nuclei where they lie in the beta stability valley. So all S process nucleosynthesis takes place there. You see there clearly the neutron capture and beta decay motion across the stability nuclei. And you can see that the first, second, and third peak in the S process coincide with the position of the closed neutron shells. Now, the R process and what it's highlighted there is one R process pathway. It's made out of equilibrium. And what ends up happening, of course, is in these closed neutron shells, there's a stagnation of neutrons because the cross-section drastically decreases. So basically the neutron cross-section correlates with abundance patterns. So you can think about, you have a neutron flow, there's a stagnation in those closed neutron shells, and that's where the abundance pattern is actually increases. And what you see there is ultimately, you made the R process and then you decay back to stability. And what you see is that those three peaks actually in the R process move to the left. No? And in some ways, there's eradication of the position of that closed neutron shell as you decay back to stability. But ultimately, those three peaks are directly correlated with nuclear structure. So what do we know about these three peaks when we looked at stars, particularly of those at low metallicity, which the R process pattern is actually much easier to extract. If you really like highly abundant R process stars, they should be your favorite, which basically in terms of relative abundances is one of the stars that have the largest relative content of gold, which is usually referred to as this Needham star. So an incredibly important finding in the last decade is that we have an incredibly robust R process, heavy R process between the second and third peak. This is incredibly important because it tells you that this process has been operated for the entire age of the universe, and that in fact seems to be not incredibly sensitive to the initial conditions, and ultimately whatever pathway we utilize to produce the heavy R process, we really have to produce these relatively robust R process. Now, we see significant scatter of heavy elements below Z of 40. There's significant scatter, so there's more variability there around the first peak. Just to get us all in the same page, just to give you a feeling of the requirements in terms of the total amount of mass that needs to be assembled, which we basically can calculate by looking at the total amount of mass in the Milky Way stars of our process. The rate that you should have in mind is about 10 to the minus 7 solar masses per year. So for a Milky Way-like galaxy that is producing about a solar mass per year of stars, 10 to the minus 7 of that needs to be produced of our process. And this is the magic number, 10 to the minus 7. Of course, if you multiply that by the age of the universe, you get about 10 to the 4 solar masses of total our process produced in the Milky Way. Now, the standard, of course, core collapse supernova happens at a rate that it's about 10 to the minus 2 per galaxy per year. And therefore, if that was to basically be in agreement with the total requirements of the mass assembly, you require a mass per event about 10 to the minus 5 solar masses. While neutron star mergers have a rate that is, of course, much lower, because you have to make 2 neutron stars and then you have to assemble them such that they merge in less than a Hubble time. The rate that it's derived order of magnitude from LIGO is about 10 to the minus 5. So again, in order to get the magical 10 to the minus 7 solar mass per year, you need about 10 to the minus 2 solar masses per event. So what are really the constraints that we can derive from these low metallicity stars? There's a very, very simple calculation that you can do, but it's relatively powerful, that says, well, if I have one of these events, they produce about a supernova worth of energy in a neutron star merger, 10 to the 51 ergs. What's the fastest that I can turn that ejecta into stars? Well, I have to wait until it cools. So basically it expands, particularly at low metallicities. All of that cooling comes from hydrogen and helium, and you have to sweep of the order of about 10 to the 3 solar masses of hydrogen before you can actually cool. So then you can actually ask, well, if I see given europium to hydrogen abundance in these low metallicity stars, what is the minimum amount of mass of europium and therefore of our process that I have to put in this region in order to explain what I see? And that gives you a minimum mass of our process that you have to produce. What I show here is a simulation of actually tidal tails expanding into the interstellar medium. And what you can see is that a lot of the asymmetries are actually eradicated. And this looks very, very similar to a supernova remnant. And what you see there in red is basically the R process material. But you immediately, by looking at the europium over hydrogen, put a constraint on the amount of mass per event. And particularly for this Needham star, you basically derive that a minimum mass per event has to be about 10 to the minus 3 solar masses. And this simple argument rules out standard core collapse supernova as the main R process, just simply from the fact that the rate is too high and the mass per event that you will require has to be small. So in order to conclude what we know from this abundance observations is to suggest that the production of heavy R process elements needs to operate incredibly robustly and at a drastically reduced rate when compared to core collapse supernovae. And that's where some of the arguments about, well, can we actually make the R process with an unusual core collapse explosion with unique conditions that happens only maybe once every 100 or 1,000 supernovae? Okay, so since here we're focusing on neutron star mergers, this is basically a broad summary of the mass ejection mechanisms. Of course, we have the tidal ejecta, which is small in mass, but it's highly neutron rich. we have in this particular case, it highlighted the squeeze polar ejecta, which is less neutron rich. And of course, the D-twin ejecta, as we heard just recently, has a wide range of YEs. So what it's incredibly interesting too is basically now the discovery of neutron star black hole events. Here I'm basically showing the mass distributions of both. And I show this really nice plot that basically illustrates whether or not you're going to have any mass ejection and whether or not neutron star black hole mergers could in principle contribute also to the nucleosynthetic output. And while one of the events is certainly relatively massive, one of the other events, could in principle produce nucleosynthetic outcomes, particularly if the black hole is spinning. And of course, the constraints on the black hole spin for this particular event are not highly constrained, but in principle, if in this particular case, the spin was high, you would have produced some, ejecta. Now, in this particular case, of course, you don't go through the phase of the supermassive neutron star phase. So something I think that we're all wrestling with, which is I think incredibly important to realize, is that when one does these reaction network calculations, and Jonah just gave a really beautiful talk about some of the complexities of this. Here, just some simple reaction network calculations with different YEs. You fix the entropy and the expansion time, and you immediately start seeing the diversity of basically abundance pattern that emanates from this. And of course, if you're really forced to have a heavy, R process that is incredibly robust, that puts some challenges as to really trying to understand how effectively we're doing not only, but also how, as we heard from Jonah, how we're doing the neutrino transport, which is incredibly important. So if you think about, the first, second, and third peak kind of as your orthogonal basis, you cannot just, combine them in various ways to get these, incredibly robust patterns. So there must be some physics that are actually forcing these events to actually produce a pattern, particularly in the heavy R process, that is incredibly robust. And that's, of course, one of the challenges that we have. Now, it's all the heavy R process incredibly robust. No, I'm showing you here the Honda star, which is actually an unusual star. It's almost like a 1 in 100, 1 in 1,000 star, but clearly illustrates that not all stars have an incredibly robust R process pattern. And you can clearly see there where you're comparing the standard sort of R process pattern from the sun and that in the Honda star, and you can clearly see that the ratio of the second and third peak in this particular case is not robust. So there are possibilities for have large variations, but those variations have to be subdominant in terms of the majority of the population. Okay, so what are the clues that we can derive, particularly from the light curve? And this is relatively challenging. Here, I show how in general we calculate the light curves. This is just to illustrate a simple RNet model. You have a radiation-dominated compact fireball, you have, of course, fighting against adiabatic cooling, you have radiation leaking out, and the key is really to try to understand the heating rate. And what I showed there is one of the preliminary calculations, sort of novel calculations that Luke Roberts did, illustrating the heating rate and basically the contribution of particular elements to the heating rate. And not surprising, the contribution at a particular times come from many elements. That leads, of course, to have a heating rate that is a power law as predicted by Lee and Paczynski. But on the other hand, it makes slightly complex the determination of the abundance pattern solely on the bolometric light curve. So from the bolometric light curve, we are much likely to, to get constraints on the total amount of mass, but it's much more difficult to really think about or derive constraints from the, abundance pattern of the ejecta. And here, basically, I illustrate some of these Kilonovae models, which ultimately do end up the bolometric light curve following the heating rate, which is an incredibly important constraint because it allows to derive the mass. But as you can see, these systems are relatively, they're not very bright. And as I will show you, they're actually difficult to constrain observationally. Okay, so, I think an incredibly exciting avenue, I think, for discovery, which is work that it's been led by Barnes and Kaysen, is really to try to understand the atomic structure of these elements, and in particular the lanthanide and actinide series, these F shell elements, which have so much atomic complexity that actually the spectra carry signatures of whether or not you have those elements, particularly because they drastically increase the opacity at optical wavelengths. So here, I illustrate how the lanthanide fraction, drastically affects the spectrum. And this is, I think, one of the reasons why we can infer in this particular event that second and third peak elements were produced, particularly because, of course, all of the opacities between the second and third peak. And therefore, really having a spectral constraints it's incredibly important, at least in terms of deriving the overall abundance pattern, and at least just putting constraints whether or not you got elements between the second and third peak, and whether or not you can constrain the ratio of the second and third peak, that remains to be seen with much more sophisticated calculations. So what did we learn from these incredible event? Well, the first thing is that the bolometric luminosity follows the heating rate fairly closely. There are issues, of course, with thermalization and how effectively are all of the decay products thermalizing with the ejecta, particularly after you become optically thin. But in general, that allows you to derive a minimum mass, which in this particular case is of the order of 10 to the minus 2. And again, if you remember the magic number of 10 to the minus 7 solar masses per year, with the rate that we derive, these events in particularly are viable avenues to actually produce the entire R process in the Milky Way, which of course the vast majority of the mass is at higher metallicity. So the assumed LIGO rate, as I was telling you, again, it's of the order of magnitude of that 10 to the minus 5, so 25 mergers per mega year with large uncertainties, and the mass that we derive is about 0.06 once you take into account the thermalization efficiency. So that implies the cumulative mass of our process elements ejected from all past events over the galactic history gives you, again, these 10,000 solar masses or so that it is required. There's, of course, then an efficiency for turning that gas into stars, which, in cosmological simulations, you derive maybe have to be less than 10%. So there's also some constraints about also how much our process material it is in the ISM and how effective we are actually turning that into stars. So one has to keep that in mind. So in this particular case, the calculations made in advance of the observations seem to really indicate that there was a significant amount of lanthanide produced in this event, particularly after the blue component. The red component is, incredibly opaque. And what that tells you is that certainly in this event, we saw elements between the second and third peak. Now, if you believe that the second and third peak, at least observationally, is incredibly robust, one starts basically taking these avenues as a serious model for producing the R process, particularly also the heavy R process. And I think a lot of the challenges now lies into really make sure that, from first principles, we can derive patterns that are similar to those that we observed. And as you see, stars are not allowing us a lot of wiggle room in terms of changing the initial conditions, which in my view is incredibly interesting. We know from short gamma ray burst, that is, if short gamma ray bursts are produced by neutron star mergers, as we know in this particular case, we have strong evidence that they are. Then, based on their follow-up likers, you can say, well, would they have been, accompanied by a kilonova-like event? And, the conclusions that people are reaching broadly is that the total amount of ejecta mass from event to event has to vary significantly in order to be consistent with the constraints that we derive from short gamma ray bursts. So at least there are some hints that, that there's variability, significant variability of these events. And as we know, there are, significant variability in the initial conditions just in terms of mass ratio, black hole, neutron star, and so forth, that naturally could lead to a large variability of outputs in terms of the ejecta. So just to finalize, I think, the future is incredibly bright. The astronomy in this era of, I call celestial cinematography or multi-messenger astronomy too. It's incredibly rich. I think we really need to find another one of these events that it's actually localized relatively precisely on the sky to start learning more about the diversity of the systems. And the sort of overall goal, as I was telling you about, is really try to understand how those initial range of initial conditions lead to a wide range of outputs, and really try to understand those outputs with the understanding that we have both significant constraints from the abundance patterns that we see in the stars, and there's also more and more interesting constraints about the kinematics of our process stars, which also are telling us about the assembling history of these systems, where they basically lied in the Milky Way, or whether or not they came in satellites. And there's a lot of really beautiful work trying to tie these sort of first principles, nucleosynthetic plus radiation transport outputs, with the consistency of what we see in the relics of the Milky Way, which of course are the stars whose lifetime is longer than the age of the universe, which helps us a lot to actually put significant constraints about the type of nucleosynthetic process that have operated in the Milky Way from the moment that stars started to begin to be produced. So the future looks challenging in terms of actually observationally characterizing these events. This is a beautiful paper by Charlie Kilpatrick, really showing the events of, the sort of efforts of the community to try to characterize, particularly this event, 1908-14. In this particular case, we, based on the mass ratios, we wouldn't expect any electromagnetic outputs. I still think that it's incredibly important that the observational community is really following these events, because of course, theoretically, there's a lot of holes in our understanding of whether or not they could, in principle, be electromagnetic signatures. The same goes for black hole mergers. But what you show there is basically the constraints. And in this particular event, if we had short gamma ray bursts on axis, we were certainly seeing it. Those are incredibly bright. But as you can see, as you go more of axis, it becomes a little bit more difficult. Yet I think the observational signatures of short gamma ray bursts are much easier to characterize. Those of the kilonova, as you can see there, where the blue and red kilonova are shown, and really the limits, are not basically constraining in that regard. So this is sort of the challenge that we face in following these events. But I think in general, we can hope for neutron star merger that it's probably better localized, and if it's closer, that in this particular event, we hope that we can actually start gaining a broader understanding from the population. And I'll stop there, and thank you for your time.
Well, thank you very much, Enrico. So I'm just going to look to see, I'm Beanie, by the way, taking over from Jeremy. Just going to look to see if there are any questions amongst participants. This is noted, just trying to dig them out from the applause marks. I don't see any just yet. Oh, there is one. Udi has a question.
Yes, hello. I would just like to comment about, you have shown the fact that at any given time there is contribution for many different elements. So it's true that it's impossible to use the output or the observations that we see to constrain any specific element, but we might be able to extract some information. So for example, if we assume that in 1708-17, the abundance pattern was similar to the sun, then it's impossible to have all our process elements in sun and have the energy output that we see, because this one is dominated by the first peak, and there is not enough energy from first peak elements that contribute at very late time. So for example, if we assume that we take just some part of the elements of the abundance pattern from the sun, we need to have only elements with A larger than 85. So we cannot learn much, but we can learn something just by having the bolometric luminosity. So it's not completely helpless.
Yeah, no, I agree. And we've been with Luke Roberts and Dan Casey, we've been looking into this. And of course, especially at late times, I think, as you said, there's some interesting contributions. I think the concern there is, of course, that you have to think about the efficiency of thermalization. What I would say, I think, is there's lots of excitement about nebular spectra, which you, of course, have talked about that too. So yeah, I agree with you that there are some, especially later spectroscopy, but of course, by then the transient is relatively faint, but there are avenues actually to start constraining at least the abundance pattern. So I agree with you that not everything is hopeless. I was just talking broadly about the constraints on the bolometric light curve, broadly speaking. But yeah, you're absolutely right that the details and yeah, we've been thinking about how the heating rate changes with with YE and with first, second, and third peak. And I think you're right that especially at late times, especially in these infrared observations, there's some possibilities of starting trying to constrain at least the ratios of the peaks. So I certainly agree with you.
Thanks.
And it's lovely hearing your voice. I haven't heard it in a long time. So.
Thanks again.
Are there any other questions? I don't see any other hands raised.
Can I say something? Can I? Yeah. I'm sorry about not raising my hand. I had some problem. I'm switched to an iPhone for some reason, and it's more difficult to operate. Hi, Enrico, and nice to hear you after a long time also. I have one other comment related to the Kilonovae light curve, which is the fact that was not mentioned, I think, in most of the talks, in all the talks that I've heard so far, is that the breeze become optically thin to some of the heat, to heating emission. For example, they become optically thin to gamma rays long before they become optically thin to optical light or to red light. So, so what is also very critical is the fission debris, how the energy is produced, because some forms of the energy are absorbed, like electrons are absorbed, and others are depending also the time, then some others are.
Yeah, certainly the thermalization efficiency is incredibly important. And I think if you follow sort of what Joanna beautifully illustrated in at least the outflows that he was predicting, there's also some interesting if the ejecta has any YE gradients across, that the thermalization efficiency may also be different location by location within the outflow. But yeah, you're absolutely right that that's an incredibly important thing to really take into account effectively if you really want to, I mean, not only to derive the bolometric light curve, but as Udi was saying, to really try to tie down the abundance with the heating rate, because that's incredibly important to make sure that you're doing calorimetry effectively. But I agree. And I actually just saw that there's 2 SVs in this talk. So. Oh,
yes, there are. Looks like the same person though.
You never know. I mean, we need to clone him, so that's a good thing. Thank you, Sven. Yeah.
Okay, thanks very much. I suppose we should probably pause for coffee now. Thank you.